how can we experimentally determine what the empirical formula for a compound is? Well, these problems are going to be referred to as UNC problems, and that's just shorthand for unknown. So UNC problems are ones in which we have some kind of a combustion device that's used to determine what the empirical formula of the compound is. And the compounds are going to contain carbon and hydrogen. They also might contain other types of elements as well. So let's look at a typical combustion apparatus. We have our unknown, or our UNC, in our chamber here. Oxygen is allowed to flow in so that all of our unknown can combust. We heat it up and combust it. Carbon dioxide and water are byproducts of that combustion reaction. Plus, there may be other gases and excess oxygen. And all of those gases are going to pass through the next two chambers. In the second chamber, we're going to contain some kind of compound that can absorb water. So in this particular example, magnesium perchlorate is our water absorber. So as the combustion takes place here, and water passes through this first chamber, it gets absorbed by the magnesium perchlorate. If we know what the mass of the magnesium perchlorate is before the combustion, and we determine what the mass is after the combustion, the difference between those two is the mass of the water that was produced during that combustion. The carbon dioxide and the excess oxygen and other gases would pass through that first chamber and into this next chamber, which would contain some kind of a carbon dioxide absorber. In this particular example, it's sodium hydroxide. So we know the mass of the sodium hydroxide before the combustion takes place. We know the mass after the combustion has taken place, where that sodium hydroxide has absorbed all of the carbon dioxide that was produced, and the difference between the two would be the mass of the carbon dioxide that was produced during the combustion. Any excess oxygen and other gases would then leave the chamber. So we know what the mass of the original sample is that we combusted. We can determine the mass of the water that was produced here and the mass of the carbon dioxide that was produced here. And that information is going to enable us to calculate the empirical formula for a compound. So let's look at an example. Let's say that we're told that 0.6349 grams of an unknown, which contains carbon, hydrogen, and oxygen, produced 1.603 grams of carbon dioxide and 0.2801 grams of water. Determine the empirical formula for the compound. All right, so let's go ahead and do that. The first thing we're going to do is write a general equation for our reaction. So we're going to write down UNC, that's our unknown. To combust things, we need to add oxygen in. And we're going to produce carbon dioxide and water. And we're going to take the information that we were given in the problem and just substitute them in underneath the formulas. So it told us that the mass of the unknown was 0.6349 grams. The mass of the carbon dioxide that was produced was 1.603 grams. And the mass of the water that was produced was 0.2801 grams. So we're going to start with the carbon dioxide, and what we're going to be able to do with that number is convert grams of carbon dioxide to moles of carbon dioxide, and from moles of carbon dioxide to moles of carbon. And we're going to assume that all of the carbon from the unknown is present in the carbon dioxide. So that way we're going to know how much carbon was in our unknown. So we're going to take 1.603 grams of carbon dioxide. And in our first step, we're going to convert from grams to moles. So 44.01 grams of carbon dioxide per every 1 mole of carbon dioxide. And then, based on that formula, for every 1 mole of carbon dioxide, we're going to have 1 mole of carbon. So that's going to give us 0.03642 moles of carbon. That's how much was in the carbon dioxide, so it's how much was in the original unknown. Now we're also going to need to know the mass of the carbon, so we'll put that underneath. We've got 0.03642 moles of carbon, and we know that for every mole of carbon we have 12.01 grams, so that would give us 0.4374 grams of carbon. And we're going to use that later on in the problem. So now let's look at the water. And we're going to do the same kind of calculation. We have 0.2801 grams of water. We're going to be able to convert that to moles of water and then moles of hydrogen. So 18.02 grams of water is equal to 1 mole of water. And then based off the formula, 1 mole of water has 2 moles of hydrogen. And that comes from that H2O formula for water. So we're going to get 0.03109 moles of hydrogen. And that's how many moles of hydrogen are in the water, and we're assuming that all of the hydrogen came from the unknown, so we know the moles of hydrogen in our unknown. We're going to need to know grams, so we'll do a conversion for that next. We have 0.03109 moles of hydrogen. For every 1 mole of hydrogen, we have 1.01 grams of hydrogen. And that would give us 0.03140 grams of hydrogen in our unknown. So now we know about the carbon in our unknown, and we know about the hydrogen in our unknown, but there's another component in that unknown, and that's oxygen. So to figure that out, we're going to take the total mass of the unknown, subtract the mass of the carbon and the mass of the hydrogen, and what's left over will be the mass of the oxygen. So we have 0.6349 grams of our unknown. We're going to subtract 0.4374 grams of carbon. We're going to subtract 0.03140 grams of hydrogen, and that's going to give us our grams of oxygen. So we're going to have 0.1661 grams of oxygen. So to figure out our empirical formula, we're going to have to convert that to moles. So 0.1661 grams of oxygen, 16.00 grams of oxygen is equal to 1 mole of oxygen. So that's going to give us 0.01038 moles of oxygen. Now when we look, we have moles of carbon, moles of hydrogen, and moles of oxygen. It goes back now to our empirical formula problem, where we're going to find out what the simplest mole ratio is, and then we can determine our empirical formula. So we have 0.03642 moles of carbon, 0.03109 moles of hydrogen and 0.01038 moles of oxygen. We're going to divide by the smallest number. So the smallest number is 0.01038. Divide everything by the same thing. That keeps the ratio the same. And that's going to give us a 3.5 to 3 to 1 ratio. That's not a simplest whole number mole ratio. And we can't just take 3.5 and round it up. So sometimes what we might have to do is multiply that ratio by some whole number to give us a whole number ratio. So if we multiply all of these numbers by 2, that'll give us a 7 to 6 to 2 ratio. And that's a whole number ratio. So our empirical formula is C7H6O2.